Hello everyone, welcome to today's lecture. In this lecture, we are going to learn about floating point arithmetic operations. So here mainly there are two floating point arithmetic operations, which is a floating point multiplication and floating point division. So let's start with the floating point multiplication. So before we start, let's understand what is a floating point number. This concept is already we have learned in our chapter number 1. So here I will revise it that any number something like this 11101.1000110. So this number will be normalized in the floating point number. So this is something like 1.1110111000110 into 10 raised to 5. So here 1 point and then this whole number, that is called the mantissa. Here 10 is the base and 5 is the exponent. So here the number is same, but here we'll represent this number in a different format, and this format is called the floating point representation of number. So that is why this number is called the floating point number. Now here we are going to learn about how to multiply the floating point numbers. And if you want to multiply these two numbers, so at that time we'll follow some algorithm. So usually mainly there are 4 steps to perform the multiplication. First is check for zeros. We have to check if there is if any multiplicand or multiplier is 0 or not. So, if both are 0, then the result is 0. If any one of multiplicand or multiplier is 0, at that time result is also 0, because 0 multiplication anything is equals to 0. So that is the first step in which we have to check for 0. The second is add exponent. In our addition and subtraction operation that we have already learned in our previous lecture, we'll normalize the exponent. Here if two number has a different exponent, 10 raised to 5 and 10 raised to 3, at that time we'll normalize the exponent and make the exponent 10 raised to 5 for both the numbers. But in the multiplication that is not the case. Yes, the exponent can be anything, and if two number has a different exponent, so that is okay. So at that time what we are doing in the multiplication, will add the exponent value. Yes, if number 1 has a exponent 10 raised to 2 and the second is 10 raised to 3, at that time in the final output the exponent value become 10 raised to 5. So that is why we'll add the exponent, then multiply the mantissa, will multiply this mantissa value and normalize the result. So these are the main 4 steps we have to follow for the floating point multiplication. Now suppose there are two numbers something like this, 0.5812 into 10 raised to 5 and 0.234 into 10 raised to 7. So these are the two numbers, and if you want to perform multiplication on these two numbers, so at that time we have to follow this algorithm. Okay, so in this algorithm the first is BR and QR register. So BR register stores the multiplicand and the QR register stores the multiplier. After that, the first step is, we already discussed that, check for zeros. If BR is 0, at that time the output is 0. So here we'll store our final output into the AC register. So if BR is equals to 0, at that time the value of AC is directly 0. And if BR is not 0, it means multiplicand is not 0. At that time we'll again check if multiplier is 0. So for that we'll again check the value of QR. If value of QR is equals to 0, it means the output is 0 for the multiplication. So at that time also we'll put the value 0 onto the AC register and directly end the program. Okay, now if BR and QR is not 0, it means multiplicand and multiplier is not a 0. At that time we have to perform the steps. So here, as per the steps in the algorithm, first we have to add the exponent. So here, as I said, that we have to add the exponent value, and this exponent value will be added through the adder. So adder value will add the data A and B, and on that adder will perform addition on register A and B. Here the exponent value of multiplicand will be stored in B, and the exponent value of multiplier will store into Q. So here we have register Q and B, and adder adds the value of register A and B. We have B but we don't have a value of A. So that is why first what we'll do, value of register Q will be transferred to register A. That is why the statement is something like this, A arrow Q. So the data of Q will be transferred to A. Now we have data exponent value in A, we have exponent value in B. So now adder adds the exponent value. So that is why the final output will be stored onto the register A. So A plus B will be transferred to register A. So this is the second step, add the exponent. After this, the third step is multiply mantissa. So here the mantissa value is 0.5812 and 234. So these are the mantissa value. So here the mantissa value will be multiplied. We already learned about the fixed point multiplication algorithm in our previous lecture, Booth's multiplication algorithm. Yes, so here this whole algorithm will be executed and the two number will be multiplied. After this multiplication process, the fourth step is the normalize result. Okay, now to normalize the result, we have to check the value for the mantissa. Suppose the output is something like 0.012 into 10 raised to 12. Okay, this is the output value. So 10 raised to 12 means that that is achieved here at exponent addition, and the mantissa result will be multiplied and it is generated here. Now after this we have to normalize this result, but how? For that first we have to check the MSE bit of mantissa. Here the MSE bit of mantissa is 0. So here if MSE bit of mantissa is 0, at that time we'll perform the shift left operation and decrease the exponent value, because if we'll perform the shift left operation, at that time this 0 will be transferred here and the output is become something like 0.12 into 10 raised to 11. Okay, suppose if you have a 0.00012, so at that time we'll shift 3 bits and will perform shift left 3 times. At that time will decrease the exponent value 3 times. Okay, so why we'll do this? Because in the multiplication there is no overflow, but there is one condition, underflow. And to normalize this result, if the first bit of mantissa is 0, at that time we can say that there is a underflow, and to correct that underflow we'll perform this shift left operation. Okay, and this is how we can normalize our final result. And if the first bit of mantissa is 1, at that time no need to normalize the result, we'll directly store the result into the AC register. Yes, and will end the program. So this is the algorithm for floating point multiplication. That's it. Thank you so much.